Okay. Good afternoon, everyone. Few announcements. The first one being that the deadline for Lab 3 is tonight. So be sure that even if you're not going to submit your project, be sure to submit your peer reviews. With regard to the quiz and the quizzes situation, as of now, I'm not planning on having a quiz this week. My entire bandwidth this weekend, almost mine and Maisy's, went to deal with the situation we had with the past quizzes. We're still in the process of finalizing a resolution for that before we even get to deciding what we're going to do for the future quizzes. Yeah, so there's a little bit of uncertainty in that aspect of the course. Once I have more to say, I'll definitely send an email to the class. I guess that's it. That's pretty much all I have. Lab 4 will be released soon. We're actually working around the clock to finalize Lab 4. Excuse me. So once we have it finalized, we'll definitely release it. Hopefully tonight, if not tomorrow morning. Excuse me. Okay. So let's continue with the course, with the lectures. If there is no questions, let me get myself out. Okay, so to recap, we are almost done with this lecture on real-time systems. We have seen quite a lot of different topics that have to be considered in designing a real-time operating system and a real-time system. So we're at the end of it. We're talking about multiprocessors and how we can design a scheduler for a real-time system that runs on a multiprocessor. So what we have seen is basically this table. We have our usual uniprocessors classes, basically a static, dynamic, fully dynamic. And due to running on a multiprocessor, we have added another dimension to this, which basically says whether or not we can migrate. And if we can migrate, is it restricted to jobs, or is it fully allowed for jobs to migrate? And as a result, we have 9 classes of scheduling policies. So for 3 of them, right off the bat, if you cannot migrate and you're going to just go with partitioning, then you have an NP-hard problem, first of all, to decide whether or not your task set is schedulable. The second problem with it is that the maximum utilization that you can get is basically half of your capacity. So if you have M cores, then you would want to be able to utilize them all the way to 100%. That would mean that you want utilization of M because you have M cores. So there is proof that there are certain task sets with utilization of M+1 divided by 2 to be the maximum achievable utilization. for any partitioning scheduler. So any scheduler in this class, at max it can achieve this much utilization. Okay, so what about other scheduling classes? So one that you might think of is dynamic and restricted class. So one example of this class would be to basically run. So basically, this class, you have your jobs have to have fixed priorities, and then you must run on each job has to run on a single CPU. The jobs cannot move around. But then different jobs within each task could be migrating. So there is no restriction in where each task runs. Each job of each task could run on different CPUs, but then once they're assigned, they cannot basically move around. And this situation might be desirable in some cases, but not in all cases. So another type of a scheduling class could be DF. Basically, again, we're going to have fixed priorities for jobs, but we're going to let the jobs to migrate between different processors. One example of this class is to have a global EDF, earliest deadline first. So you have one instance of the scheduling policy, which is EDF. You're going to have a single queue that is going to assign jobs on CPUs, on all CPUs. But as you can see, because you're using EDF, the type of a scheduling policy is D. It's dynamic. But then because you're allowing preemption, a job could be preempted on one CPU, and next time that it's going to be executed, there is no guarantee that it's going to be executed on the same CPU. So basically, you're allowing jobs to fully migrate between CPUs. But it's not hard to see that even this optimal scheduler for uniprocessor, EDF, is not going to be optimal for this case. There is an example here, as you can see. I'm not going to go to the details of it, but you can check it out. You can see that EDF, although being optimal for uniprocessor, when you apply it to a multiprocessor, it won't be optimal anymore. And then you might think of SF, basically something like a global RM to get S, which is a static. And again, because you're preempting jobs at any point, it's fully dynamic. Jobs could migrate. And again, you can also see that this is also not optimal. And there is another theorem that extends the theorem that we saw in the previous slide. It says any XY based scheduler where X and Y are not F, so any other type of a scheduler other than FF based scheduler, the maximum utilization that they can achieve is m+1 divided by 2. So all these classes, they have the same restriction that that we had previously. Okay, then let's focus on FF. The first thing that might come to your mind is, okay, instead of to get this F, first one, fully dynamic, we can use LLF, something like a global LLF. And then, but then unfortunately, even if you use a global LLF, the same way that we talked about global EDF, it's not going to be optimal. So at this point, you might think, okay, is there any optimum or optimal scheduler for a multiprocessor? And the answer is yes. Fortunately, there is. The scheduler that is optimal for multiprocessor is called P-fair scheduler. And the idea is to basically allocate CPUs between the tasks such that we can enforce some notion of proportionate progress. And we'll see that it's actually proved to be optimal if you go with this, for both for uniprocessor and multiprocessor. And it can produce feasible schedule for any task set that has a utilization that is less than M. So basically with this scheduler, you can achieve all the way to M utilization. You can utilize all your processors. Let's look at it. It requires some definitions. The main idea of this scheduler is for each task I, we're going to assign a weight that is proportional to its utilization. So, or actually it's equal to the task's utilization. So the weight that each task gets, it's basically its utilization, EI divided by PI. Now we're going to divide time into a small time quanta, and the rest of this slides on P-fair, we're just going to assume that we're dealing with integer numbers because we have divided time into quanta. So the first quanta is going to be 0, then 1, 2, 3, 4, 5, 6, right? So everything, even the parameters of each task, basically their deadline, their period, all of that are going to be noted as a multiply of the time quantum. I got a question. So how do we quantify M is a given instance of utilization on a scale of 0 and 1? So, okay. So if you go back to the previous lecture, we said that so M basically is number of processors that we have, and N is the number of tasks we have. So each task, the utilization of each task basically means what portion of CPU time they require. Now, in total, we have M CPUs, so we can accommodate up to a total utilization of M. So each one of them, each task has a utilization between 0 and 1. Now we add them up all N tasks, their utilization. If it is less than M, which is the number of CPUs we have, then P-fair can schedule that task set. Okay. Now, so everything is going to be in integer. So now EI execution time is going to be a multiple of the time quantum. So is period, so is deadline. Now we're going to define lag for each task, and a lag captures how the task is with respect to its fair share. So if we are going to give CPU time to each task in proportion to the task's weight, then at time t, task I should have received t times wi time unit on the CPU. Now we subtract how much it actually got. So this is how much it should have, and this is how much it actually had already received. And the difference is basically the lag. So if the lag is positive, it means that this task needs to get more CPU time. And if the lag is negative, it means that it has already received more than its fair share. Now, a couple of definitions. We say a schedule S is periodic if and only if for all tasks and any integer k, the allocated amount of CPU to task I at time k times pi equals k times ei. So after k period for task I want task I to receive k times ei time units. And if this is true for all k's, then it means that the task received ei at each period, which means the task was scheduled periodically. So it actually received its execution time for each period. Now, a schedule is p-fair if and only if for each task I and time t, the lag is between -1 and 1. So it never gets to exactly 1 or more, or -1 or less. So it's always a number between -1 and 1. So that's the definition of p-fairness. It's just a definition. Now you can show properties of any schedule that is p-fair. One thing that you can definitely show is that if you have a p-fair schedule, then you also have a periodic schedule. And that's easy because if lag is always between -1 and 1 for any I and any t, you can set the t to be a multiply of tasks period. Then this lag at that time should be between -1 and 1. But the thing about it is that at that point, this element of lag is an integer. If t is a multiply of period, then w is ei divided by pi, so pi's would cancel out and everything left is integers getting multiplied by each other. So this element is an integer. Allocation is also an integer. Allocation basically says how many time quanta you got on CPU, so this one is also integer. So an integer minus an integer is an integer, and the only integer number that lag could be is 0, because it cannot be -1, it cannot be 1. So the only integer number for lag is 0. So basically that means that t times w becomes the allocation. So as a result, allocation equals k times ei. But vice versa is not true. It's very important. You definitely have to think about it. So if you have a p-fair schedule, then you have a periodic schedule. But if you have a periodic schedule, then you don't necessarily have a p-fair schedule. And to just give you an idea why, and this is a very important why, is that you could potentially get your EI. So for periodic, in order for a schedule to be periodic, all it requires is that each task gets EI every period. But it doesn't put any restriction on when you have to receive your EI. So basically, you could potentially receive your EI at last minute. So right before your deadline, you finish your EI. But that situation means that at the beginning of your period, you didn't get any CPU. And for those times that you didn't get CPU, this lag could violate this condition. So there are certain T's before you start getting your CPU time where your lag actually becomes positive, more than 1. And that violates the condition for p-fairness. So although you're still periodic, but you're not p-fair. But again, the other direction always works. So if you are p-fair, then you definitely are periodic. Now, so let's make some more definitions with regard to pfair tasks or pfair schedules. We're going to divide each task into quantum-sized subtasks. So if the execution time, worst case execution time of a task, EI, is let's say 5, this means that this task has one job of length 5 in its period, every period. Now we can divide this job into 5 subtasks, so basically it has 5 subtasks if its execution time is 5. And then next period we have another 5 subtasks. And then next period we have another 5 subtasks. So after 3 periods, this task should have had 15 subtasks. Okay, so now we're going to denote Tij to be the jth subtask of task I. Okay, now we're going to define a pseudo release time for each of these subtasks. So basically this is the earliest time that this subtask Tij could be scheduled under a pfair schedule. And how do we calculate this? Well, release time of the jth subtask of task I is the minimum time that the lag is going to be more than -1. Because the lag always has to be between -1 and 1. So this is going to be the minimum time that we want the lag to be more than -1. And if you just solve this, you can get that the release time for the jth subtask of task I is j-1 divided by wi, the floor of it. Now we're also going to define a pseudo deadline for each subtask, and that would be basically the latest time by which Tij must have been scheduled. And if you don't schedule it, what does it mean? If you don't schedule Tij by a certain time, that means that at that point, at that time, you have basically at max scheduled j-1 subtasks, because you still haven't scheduled the jth one. So at max, you have a scheduled j-1 tasks. So here we say, how do we find out what that time is? So we say we want to find the maximum time by which, if you haven't scheduled the j-1 task, then you're going to violate the lag condition. So the lag would become less than, it will become more than 1 or more. So we want to find the maximum time by which we could potentially postpone running Tij. So the lag is still less than -1. And if T increases and we haven't done it by then this becomes more than 1, and we're going to be violating the lag condition. And if you solve this, you will see that it's going to be the ceiling of j divided by wi. Okay, so now we have a pseudo release time for each subtask and a pseudo deadline for each task. We're almost there. Now we only have to now define a window that we can run each Tij, each subtask. So basically, that window will be from its release time to its deadline. And some of the interesting things is that if you look at these release times and deadlines for consecutive subtasks, so for subtask J and subtask J+1, the deadline of subtask J is either exactly the same as release time of subtask J+1, or it's different just by one. So it comes one time quantum after the release of the J+1's subtask. So they're either equal or they differ by one. So here is an example. So let's say you have a task with a deadline or period of 6 and execution time of 5. So this means that at each period you're going to be having 5 subtasks, right? Now, if you just put J, so WI is basically 5 divided by 6. Now you just change J to get the window for each subtask, and I've done that calculation for you. As you can see, the window of subtask 1 is from 0 to 2. So this subtask has to be executed in this window if we want to have a p-fair schedule. And the rest of them are as follows. So the 5 subtasks in the first period have to be executed in these windows. And as you can see, they all have overlap of 1 in this case. In some cases, they might have no overlap. In the case where the deadline and release time are the same, then you won't have overlap between windows, between 2 consecutive windows. And then the rest of them for the next period for subtask 6 and subtask 7, as you can see. Okay, now how can we prove that a p-fair schedule always exists? So the way to prove it, I'm going to show it with an example. You can extend this example to cover any general case. Here I'm going to do an example for scheduling 3 tasks, T1, 2 and 1, 6 and 5, 3 and 2. If you add them up, so this one, the utilization is half. This one utilization is 5/6, and this one the utilization is 2/3. And if you add them up, the sum of the utilizations come up to become 2. And let's assume that we have actually 2 CPUs, so the utilization is exactly the same as what is available. Here is how you can prove that the schedule exists. We're going to do it for the greatest multiply of the periods. So 2, 6, and 3. We're going to, because it's periodic, because p-fair scheduling is periodic. So if we show that it can schedule all the tasks in a period of time that is as long as 6, then it just repeats itself. So now we have time quantum 0, time quantum 1, time quantum 2, all the way to time quantum 5. And at each time quantum, we can actually schedule a utilization of all the way up to 2. That's why you can see here 2. Now let's start from the beginning. This is a network flow. For those of you who are familiar with the topic, so we have nodes here, and then we have edges. Each edge has a capacity, how much flow can go through that edge. Now at the beginning, to the source, we apply a load, and then we want to see what is the maximum load that can come out of the network flow. So now here what we're doing is we have 6 periods, and utilization is 2. So we want to schedule 2 times 6 tasks, basically. So that's the load that we're sending. Now we have 3 tasks, T1, T2, and T3. Now the number here, T, is basically how many subtasks each task can run in this LCM. of 2, 3, and 6, the largest common multiplier of 2, 3, and 6, which is 6. So T1, because its period is 2, and in each period it runs one subtask. So if you run this for 6 time quanta, then you can run 3 subtasks of T1. For T2, it's going to be just one job, which would have 5 subtasks. T3 will run 2 jobs, each one of them 2 subtasks. So that would be 4 subtasks. So here we have T11, T12, T13, and then T21 to T25, and T31 to T34. Now, each edge from the source to the task will have the number of subtasks. The capacity will be the number of subtasks that task is going to run. And then from here on, every edge, all these edges, and all these edges, their capacity is going to be 1. Now, what is this? Why did I connect T11 to these 2 time windows? Is because this is the window of T11. So we do the calculation, we calculate the window of each subtask, and we just connect that subtask to its window. So, and now, as you can see, this is a network flow, and all the edges have integer capacity, and the load that is introduced to it is also integer. Now, there is a theorem that you can prove. It's called the integral flow theorem, that says if you have a network flow where all edges have integral capacity, then you would have an integral maximum flow, and it would always exist, the maximum flow. And what does that mean? Well, basically it means that I can flow all this load through this network and assign an integer load to each one of these edges. Well, if I do that, that means that I'm going to actually schedule all of these. Because if you can see each time here, on each time, I have connected it to 3 units here, which tells me, am I running T1 at T0? Am I running T2 at T0? Am I running T3 at time T0? So each time I can be running any of these, but then when I'm going from time to the destination, my capacity is 2. I only could run 2 subtasks. So I will decide whether run T1 and T2, or T1 and T3, or T2 and T3 at this time unit. So if I have an answer to this network flow, I basically have solved the network flow problem. Now, let's talk about pthread. So that was the proof that it actually exists. Now, it's not a good way of finding it, though, constructing that network flow, because it's very costly to solve, and there are exponentially many edges and nodes. So it's not an optimal way, an optimal way of finding a schedule. So how do we do it then? So there is a really nice algorithm which resembles earliest deadline first. Now we will call it earliest pseudo deadline first, because now for each subtask we have pseudo deadline. And what it does is basically it assigns priorities to any ready to execute subtask. And a subtask Tij will have a higher priority than subtask Tmn if the first one is the deadline of Ij is less than the deadline of Mn. So basically this subtask has a lower deadline or earlier deadline, well, or earlier pseudo deadline, sorry. So we'll schedule this subtask. If they have equal deadlines, it could happen, equal pseudo deadlines, then we'll just look at the overlap of the windows in each one of those tasks. As we define Bij, which is the overlap between the windows, is either 0 or 1. So if one of them has an overlap 1 and the other one has overlap 0, then we will just schedule the one that has a higher overlap. If both of them have overlap 1, so none of them has overlap 0, if both of them have overlap 1, then we look at the next subtask in that task. So we will look if we can say anything about subtask j plus 1 and subtask n plus 1. And if none of these happen, so if two tasks, Tij and Tmn, have not met any of these constraints to get a higher priority, then we can just do arbitrary tie-breaking rule to pick one of them. It doesn't really matter. The intuition here for choosing the one with higher Bij, basically having overlapping windows, is that if you have such a task, it means that you should actually run this task as early as possible, because if you push this task to its pseudo deadline, it means that you have less time now to run the next subtask, because the windows of the next subtask has overlap with the windows of this subtask. And if I run this subtask at the end of it, it means I can't be running the next subtask at the beginning of its release time. So I try to basically minimize the this effect by scheduling the ones with lower with higher overlaps between their windows. Okay, so pfer exists. It's optimal. It can actually solve the problem in it can schedule our task set polynomial time. But unfortunately, there is one big downside to it. It's not practical because it has a lot of overhead. So as you can see, we're making decisions on the granularity of subtasks, basically one-time quantum. And we're not making any guarantees on where each one of these subtasks are running. So a subtask, each subtask could be running on different processors, and that would mean that a job could be running on multiple processes during its execution, and that could potentially mean a lot of overhead in terms of scheduling decisions to make, and also lack of cache reuse and all those problems that we faced in the past when we were talking about different scheduling policies. So there are some extensions to pfer scheduler to mitigate some of these problems. Oh, one problem that I didn't mention is the synchronization problem. We definitely need to synchronize all the CPUs because we want to make decisions at time quantum on all CPUs. So we somehow need to synchronize all of them so that we can make decisions at each one. And these are basically meaning that, well, it's not practical. It's theoretically sound, but it's not practical. So it gives us a good benchmark, but we have to find other solutions. And there are actually some extensions to PR to mitigate some of these problems. Okay, so that's basically our lecture on real-time systems. Now, the next topic that we're going to cover is basically address translation. So just to recap, we're talking about operating system, and operating system as an illusionist and a referee has to manage resources for us. So one of the things that we've seen so far is how we can create this illusion for our processes that they're running on their own dedicated processor. So we're hiding everything about preemption and running on different CPUs. So from the perspective of the process and the programmer, this task is basically running sequentially on a dedicated processor. So that's basically what we've talked about so far. Another illusion that processes have is that they have their own address space. So they have, let's say, if you're running on a system on a 64-bit system, each process has the illusion of having a memory with capacity 2 to 64 bytes. In reality, though, first of all, you have few processes to run all your, few processors to run all these processes. And you also have a limited capacity, memory capacity. So scheduling is what we've seen so far to deal with processors, part of this illusion. And this time, on the coming lectures, we're going to focus on the memory management side of it. How can we create this illusion that each process has its own dedicated memory? What are the goals for memory management subsystem? So the main goal is protection. We want to protect the kernel from user space processes. We want to protect user space processes from each other. We want to be able to give special accesses to different data structures and different portions of the memory address space. We also want to be able to share data, although we have protection, but we don't want it to be so restrictive that processes cannot share data. So we want to have protection, but at the same time allow processes to share data. What are some of the scenarios where sharing data is important? One is basically when you have two processes running the same binary, the same code. An example of which is basically when you fork. So when you fork, both processes are running the same binary. Each one of them is running a different part of it, but the code is shared between the two. Another one is when you want to have inter-process communication. That's another area that you want share memory, basically sending messages to each other. Using a shared memory to communicate. It's different than sending messages. I take it back. So something like you both can read from the same file, or you both can read from the same memory, and that's the way of communicating. That's one. The other one is memory mapped files, which we will talk about a little bit later in the course. So you might want to map a file to a memory location. And instead of calling open and read and write system calls to read or write data from and to your files, it might be better to map it to memory and do usual load and stores to read and write to and from the file. And what if you have different processes that want to do this to the same file? So both, like you have 2-3 processes who are working on the same file and they want it to be memory mapped, it would be appropriate to only have one copy of this file in memory instead of multiple copies. And that potentially means that all the processes have to share the memory. And then last but not least is user level system libraries. Something like C library, you don't want to have multiple copies of it when every process is using it. You only want to have one copy of the code of the library, and then you want everybody to use the same copy. And that basically means sharing. The other aspect of memory management is allocation. We want to allocate memory capacity efficiently. We want to avoid memory fragmentation. And as we will see, at some point, we will have to evict memory blocks for different processes. We want to do it as least as possible. Okay, so before getting into the details of this lecture, let's just have a background, have a discussion on the background of bits and address spaces and all. Let's say you have an address space. Let's start with this. Let's say you have a variable which has k bits. Now, using these k bits, how many different things can you point to? So because you have k bits, that means you can point to 2 to k things. Now, if these things are memory bytes, then you have memory address space. Then you can have, with k bits, you can address 2 to k bytes of memory. Now, just as an exercise, what is 2 to 10 bytes? We're going to say 2 to 10 bytes is 1024 bytes. We're going to call it 1 kibibytes. This is not kilo. It's called kibi because the base is not 10. The base is 2. So just don't make a mistake. It's not. So when we say 1 kibibyte, I'm actually going to, during the lectures, it's weird to say kibibyte. I'm going to say kilobyte. But know that what this I means here is that 1 kilobyte or kibibyte is 1024 byte, not 1000 bytes. It's not 1000, it's 1024. Now, how many bits do you need to address every byte of a 4 kilobyte memory? So you have to start with 4 kilobytes is 4 times 1 kilobyte, which is 4 times 2 to 10 bytes, which is 2 to 12 bytes. So you have 2 to 12 bytes. For each one of them, to address all of them, you need 12 bits. So if you have 12 bits, you can address 2 to 12 bytes. And so on and so forth. What if you have 20 bits? What if you have 32 bits? What if you have 64 bits? How much memory can you address? The last one is an interesting one. So if you have a system, when you say my system is 64-bit, what that means is that your address bus, the size of it is 64 bits. And the whole discussion here in this slide is that if you have 64 bits, then you can address 2 to 64 byte of memory. And what is that? So what is 2 to 64 byte of memory? That is basically 2 to 34 gigabyte, 2 to 24 terabyte, 2 to 14 petabyte, 2 to 4 exabyte, exabyte, not exabyte, or xb byte, whatever that is. Pebi byte and then exabyte byte, whatever. I'm probably pronouncing them wrong, but anyways, so this is a huge amount of memory. And if you go and buy memory today for a server, for instance, at most you could get 1-2 terabytes of memory, and that would be a super, server. What your programs can actually address, though, is 2 to 24 terabytes, which is a lot more than 1 or 2 terabytes. So this is how much memory our processes think that they have. So that's their illusion, that they can address this many different things. In reality, though, when you buy a system, it has, a limited capacity in terms of memory. And this is the job of the operating system, to deal with this illusion and create this illusion without disrupting the process from running. So if you recall from lecture 2, we talked about address space, which is set of accessible addresses and their state. The physical memory is basically the data storage medium that we have in our systems. And then for each byte of physical memory, we have an address. We have a physical address. And then we have virtual address. So look at the way we talk about it. So if you have a system with 4 GB of memory, that means that you have 2 to 32 bytes. And that is basically 4 billion different addresses, close to 4 billion. Now, if you have a 64-bit processor, as we saw in the previous slide, you can actually address 2 to 64 bytes, which is 18 quintillion different addresses. More than that. So it's more than 10 to 18 different addresses. Compare this to this. So if you have a system with 4 GB of memory, but if it is a 64-bit system, your processes think that they can address these many separate memory locations, whereas you have actually in reality 4 billion physical memory locations. Okay, so let's start by what time is it? I could potentially give 2 minutes break before I continue. So let's have 2 minutes of break and then I'll continue. Okay, we're back. So let's look at the process of getting a program ready to execute. So it starts with having a source code. So basically you need a source code to start with. Then you compile. So that compile phase, you get your source code as an input. You create an object file. This object file unfortunately has incomplete information because the compiler doesn't have any information about other object files or other source codes that you might be using. Let's say you are using printf in your code. The code for printf is somewhere else. So the compiler doesn't really, when it's compiling your code, it doesn't know where that is. So it just uses some indirection method in some tables to later on find the address and code for this function. So at the time of compiling, it has only information about your source code, but it also doesn't know where in the physical or even virtual memory this code will be put, right? So everything at this point is going to be relative. Any address that the compiler creates is going to be relative at this point. It doesn't have any idea where the code goes or where the other codes are. Then you have the linkage editor, which takes a bunch of these object files and then combines them to a single relocatable and executable image. So it would rearrange, let's say, it would rearrange the code and the data in your object files. Let's say each one of them has code section and data section. It will put them all together, rearrange them, gives them, changes the addresses that each one of them had in their own object file to have a unified version of all of them in one file. Then you have the loader, which is usually part of the operating system in many cases. And the job of it is to just get an image, load it from the disk. It's a store on the storage system, bring it to the memory, and get it ready for execution. So here is where you actually bind your code, your executable image to your virtual memory, say where each component goes. And you're allocating memory if you want to run it. Now you're also allocating it memory, physical memory, and you start running it. So, or you're basically ready to run. Now, when you start running, there might be some dynamic linkage going on. So there might be some shared libraries that you've used. Let's say the C library, you used it in your code, and in the linkage editor section, we don't want to bring the object files of those libraries and put them in one big object file. The reason is we don't want to have multiple copies of these libraries. So these are shared libraries. We just want one version of them. So at this point, we cannot, at the linkage editor point, we cannot do anything because we don't know where they are in the memory. So we have to wait until right after or right before we start execution. And that's when we know what libraries we're using. Maybe you have a printf in your code, but you never execute it. So there is no need to link the library code to your code, right? So we will just in some cases, wait until the function is called, the function from the library. And at that point, we look at the memory. We see if the library exists. Then we just link the library to our virtual space. And if it doesn't exist, then we'll bring it to the memory, and then we'll link it to our virtual address space. Now, to just give you a better idea of what I mean, we're going to look at an example that we saw again at the beginning of the course, which talks about the address layer, virtual space layout of any C program. So the binary code, all of this code as a binary code, exists at the bottom of the address space. Then any variable that is initialized, it would be placed right after the binary code. And then any variable that is not initialized beginning goes after. Your heap is after these three components. Your arguments is at the top. Then your stack resides on top, and they would basically grow in opposite directions. Now, you have shared libraries like stdio.h and stdlib.h. Anytime that you actually execute a function from those libraries, they're going to be mapped to somewhere in your address space, in your virtual address space. So the operating system or the dynamic loader, the dynamic linker, is going to look at your virtual address space, find a place for that library, and then map the addresses for that library to your address space. And that is here in between the stack and heap where it comes. Okay, so again, another recall from the beginning of the course. The execution cycle that we saw included fetching an instruction, decoding an instruction, executing an instruction, writing back the results either in the registers or the memory, and then finding out where the next PC is. This next PC could be a function call. If you call the function, it could be a return. You're returning to somewhere. You're returning from a function, or it could be branches. So you're jumping somewhere, or if it is a branch. So that's the next PC. So I usually ask students, how many times do you think we access memory for every instruction that we run? For every single instruction that we run, we at least access memory once to get the instruction that we want to execute, right? This is the first time we are going to go to memory to fetch the instruction. So we have an address. What is the address? It's PC. So PC is pointing somewhere in the memory. What is inside PC? It's a virtual address of the code that has to be executed, or the data that has to be brought in. If you have a load instruction, you probably have a data, have an address. So that's the first one. The second place that you're going to access memory is when you have calculated your result, and let's say it was a store, or if it was a load. So now you're going to go back to memory and bring data, or write data back to memory. For a single instruction, you might access memory multiple times, as you can see, right? So that's something to keep in mind as we go forward. That for every single instruction, at least we're going to access memory once, in some cases more. And we're going to categorize these. So we're going to have instruction references where we want to access instructions, and we're going to have data references where we want data, load or store data in memory. Okay, so let's see different paradigms in memory protection and memory translation. A little bits of history, elements of history, but not all of it is actually history. Some of it, we still have it. Essentially, you're actually right now dealing with. Basically, your project is actually the first one, a uni programming, where you don't have protection, you don't have translation at all. So the whole image that you're loading into your device is just one big program, and you're running it, right? So when it comes to general purpose operating systems, some of these things are just history. When it comes to embedded systems and real-time systems, some of these topics, some of these styles and paradigms already exist. So again, keep that also in your mind. So back when computers started, you had these computers that would run only one program at a time. And for these programs, you basically would put them in the same place in physical memory, and they would have access to everywhere because they were the only program that was running in the memory. So there was no notion of virtual address and physical address. They were just equal. You had only physical memory to access. And basically what you had was something like this. So you had the operating system code and then the user process code here. All of it residing in the same address space, which was physical address space. Then we had this shift to multiprogramming, again, without protection and translation. So this time you would have the operating system code and the user processes codes residing in the same address space. Probably each process would be loaded at a different address. This is the one that you're actually doing, right? You have you're creating tasks. Each task goes somewhere in the memory, but all of the tasks can access each other's data in reality. They all have access to physical memory. There is no notion of virtual memory. So everybody has access to the entire address space. There is no notion of virtual memory. So this is basically what we have. And this is, if believe it or not, was the case when Windows started. Microsoft Windows, like the earliest versions, were something like this. And if there is any bug in any of your processes, they could crash your entire system. They could actually change the operating system's memory. They could interfere into operating system's memory. There is no protection, and everybody sees everybody else's data. Then at some point they realized that this is not a good idea, so let's have at least protection. The way to do this without memory translation was to introduce registers called base and limit for each process. So we still have one big physical address space, big or small, doesn't really matter, but we don't have a notion of virtual address, but we're going to limit where each process can access. So we're going to allocate some bytes, a portion of physical memory to each process. And every time the operating system loads or starts running that process, it just sets these two registers, the base and limit, with the physical addresses associated to this process, saying that, okay, this process can access any physical memory between these two addresses. And every time a process would violate this, would access somewhere outside of this this limit, then you would raise an exception. And it was the job of the operating system to load these registers, as I said, and it would just save them into the PCB. Every time a new process comes, these registers would change. Now, this is kind of like for general purpose operating system. This is kind of history, as I mentioned. Now, what is a better way of doing this? Well, the better way to have protection is to use address translation. So let's give processes different virtual address spaces, but then have mappings that would take a virtual address and turn it or translate it to a physical address. That way, the operating system, without processes knowing, can provide protection because all this process sees or generates are just virtual memory addresses. And by mapping different virtual memory addresses to different locations, I can make sure that nobody can access anybody else's, because this is a level of indirection. They're not going to see this mapping. This mapping is only seen by the operating system. And as long as they don't share anything on the physical address space, they cannot see or access each other's data. And if it happens that I want them to share data, I can basically map their virtual addresses to the same physical address, which we'll see later on. So that's the idea. Now, there are a lot of details in how we can implement these translation maps. One thing to note, very, very important, is that we're going to need this translation map every instruction that we run, because we're going to do an address translation every instruction, because we need to go to memory every instruction. So whatever cost that this introduces, it's going to be added to every instruction. So we have to be really careful to minimize the cost that this address translation is going to have. Okay, so let's see why this is a good idea to have, why providing protection through address translation is a good idea. So the good side of it is that you can compile, link, load your code independently. They don't need to know anything about where in physical memory the code is going to be. So the compiler, the linker, the loader, they don't really need to care about physical memory. They all work with virtual memory address space. And then the operating system can map each image to any part of or portion of physical memory without even letting the process know about it. The other thing about it is that you get protection for free because of translation. As I said, if processes cannot see each other's data, they cannot access it, they cannot change it. So you have protection. And as again I alluded to, you can have memory sharing by mapping two separate virtual addresses to the same physical address. Now, what is the downside? The main downside is performance overhead. So now for each instruction, we're going to just do the translation. And if we're not careful and the translation overhead is high, then we're going to introduce it for every instruction, and that could be detrimental to the performance we get. And also, depending on how we do the translation, we might need extra hardware. And having extra hardware basically means having more area, having more power consumption, and potentially lower performance, because as our processors get bigger and bigger, you need to distribute cycle, and that means that the frequency of your cycle should go down, and that is basically making your processor slower. So basically, that's one of the reasons we want as low hardware as possible. Which time do I have left? Okay. Okay. The simplest address translation that we're going to see is very similar to the base and limit case that we saw. Now we're going to just apply the same idea to the virtual and physical address. So we're going to let's assume that our processes can see anything between 0000 and 10000. So this is a virtual address space for one process. Let's say that operating system decides to map this virtual address space to this physical address space. So as you can see, this is virtual address. Now we mapped it to physical memory. So it has now physical address, which is different than the virtual address that we had. So all we need to do is basically have a base and bound registers. We're going to say the base of this process is 1000. So we put the base here in the base register, and the bound register will be basically how much memory this process has. So it's a relative number. What is the maximum address that this process has access to? Now, every time this process makes a memory request, we check that memory location. It's going to be a virtual memory address. We'll check it first with the bound. If it is more than the bound, then we're going to raise an exception. But if it is not, then we get the virtual address, we add the base to get the physical address. So as you can see here, in this process, we are doing a translation from virtual to physical address. So with to just put this into perspective with the previous one, which was just protection without memory translation, our process would still generate physical address. Here, the process only works with virtual address, and we're just translating it to physical. So let's discuss this. What are the pros and cons of this? Actually, that would be next slide. But here, let's have some discussions. So every process in this way we're basically providing that illusion, right? By giving them virtual address, they think that they can access anywhere inside that virtual address, and we're just going to map it to physical address. So they think that they have dedicated memory starting from 0000 to whatever their address space is. Now, one thing to note here is that we're mapping each process to a contiguous region of physical memory, and that could be a problem. We'll see. The virtual addresses do not change if we relocate the process inside our physical memory. That's a good thing. But in general, the good things about this is that we're getting protection. We're getting that illusion implemented. The other good thing about it is that the translation is really low overhead. All we're doing is comparing with the register and adding a base. So it's minimal amount of work that you could do. So these are good things. Now, what are the bad things? What happens if you want to expand your address space? What happens if you want to expand your heap and your stack? What happens if you want to have memory sharing? Is that possible to share memory? The answer is no. I think I have a slide later on coming, but here to give you an idea, because each process has a structure, well, you know, at the top of your address space, you have your environment. At the bottom of it, you have code. Now, with the base and bound method, if you actually share memory, then somehow your stack would be mapped to somebody else's code section or data section. So it's almost impossible to share a stack, for instance, or share heap or share data, because they're in a fixed location in each virtual address space, and the sharing is very coarse-grained. So that means that you cannot practically share. Even if you share memory, that wouldn't be practical. So if you see in any quizzes, can you share memory in base and bound? The actual answer is no. I mean, although you can technically share, but that is not a practical sharing, because basically you have your stack is mapped to somebody else's code, and that is not acceptable. And it also leads to memory fragmentation. So yeah, I talked about this. So what is fragmentation? I think I'm going over time. Okay. So anyway, I'm going over time, so I'm gonna stop here. I'll continue talking about base and bound in the next lecture. Okay. So with that, I end this lecture. Thank you for all those who attended the lecture, and we'll talk to you next Friday. I mean, coming Friday. Take care and be safe. Bye-bye.